Hi, everyone. So there are three of us. I'm going to cover the TCP transport part. Although we have Fred and David here who contributed just as much as I did to having this. So thanks a lot to Fred and David. So why did we add the TCP transport binding? Well, we had PCIe, which is the de facto transport for direct attached SSDs, but it doesn't scale for something like disaggregated storage. And we then added fiber channel and RDMA, which are awesome if you have a fiber channel network or an RDMA capable fabric. But if you don't, you probably have a TCPIP capable fabric. So it just sort of made sense to add this as a viable option to have something that's efficient host and controller interface that's going to be end-to-end NVMe or NVMe over fabrics, and it's going to run on pretty much any network out there that's not in the form of 3. So if you look at this different transport and their characteristics, we can segment those into 3. We have PCI Express, which basically all the interface is memory semantics, right? The host reads and writes to host memory buffers, which are the submission and completion queue, and maps data buffers to the device, which fetches basically from host memory all the data. We have message and memory combined model, which is typical for RDMA, where submission and completions or NVMe over Fabric's command capsule or response capsules are sent using message semantics, right? They're message sent from the host to the controller and back. But data buffers are still mapped with memory semantics, right? We basically give out a handle that the target does remote direct memory access to the host. And the third model, and surprisingly or not, TCPIP, while running on Ethernet like RDMA, actually shares the same model with Fiber Channel, which is all messaging models. So both the command and response capsules are sent using messages, but also the data transfers is a message semantics sort of interface. If you look at the queuing model or the queue mapping for NVMe over TCP or the TCP transport binding, basically every submission completion queue pair, NVMe submission completion queue pair, are mapped one-to-one to a bidirectional TCP stream or a socket, however you want it to be. And that's map one-to-one to every individual queue. So you don't have aggregation of queues that map into a single stream, or you don't have a single NVMe queue that maps into multiple TCP/IP streams. Basically, the scaling or the parallel channels are scaled with NVMe queues, each mapped to one-to-one to a bidirectional TCP/IP stream. So basically, NVMe or TCP or the TCP transport binding simply defines the way that every NVMe payload that is transferred across the wire. We call it NVMe TCPPDUs, which stands for protocol data units. And either NVMe over Fabric's command capsule or response capsules or data payloads, usually on the wire, will look in this form. We have, first of all, the header, which is split into a common header that says basically which type of payload we have within the PDU itself. And then we have a PDU-specific part header, which can either contain, for example, the NVMe over Fabric's command capsule or the response capsule, or it can have some metadata or a header that's specifically designed to describe the data payload itself. Behind that, we have optional header digest, which is a 4-byte CRC32C data integrity part that protects the header and protects the TCP stream, keeps it in sync, and validates the correctness of the data. After that, we have an optional padding space that's designed to accommodate maybe offload devices that may have alignment constraints. After that, we have the data, should it exist in the PDU itself. We have the entire data that the PDU consists of. Follow that, we have a data digest, which is, again, a CRC 32C 4-byte digest protection. So I think overall we have 9 different types of protocol data units or type of messages that we transferred in the TCP transport binding. We have, and they can cluster into 4 topics, I guess. The first is the connection initialization part, where both the host and the controller negotiate and declare different parameters or capabilities that are specific to the TCP transport binding. That obviously can succeed or fail, or let's say converge on an agreement. We also have the terminate connection part. There are 2 distinguished NVMe PDU types. We have the host to controller, that's the H2C, terminate request, and the control to host terminate request. And these are basically PDUs that are designed when the TCP connection is sort of torn down in a non-graceful fashion, and they're used to communicate diagnostic or information about what went wrong. After that, we obviously have the command capsule PDU and the response capsule PDUs. That basically their payload is the NVMe Fabrics command capsule and the response capsules. And then we have the data transfer related PDUs, where one is host to controller data PDU, which basically is a PDU that consists of user data payload, and control the host. When the host wants to read data, the controller will send it control the host data PDUs. And we have one special type of PDU that's called an R2T, or ready to transfer, and that basically is the NVMe TCP credit mechanism that basically gives the controller the ability to control the amount of incast that it sees from the host side. So how do you form an NVMe queue that sits on top of a TCP transport binding? Obviously, the first part is to establish the TCPIP connection. That's a 3-way TCP handshake: SYN, SYN-ACK, and ACK. After that, we have our initialized connection request and response PDUs, which basically form an NVMe TCP connection. And after that, we have the NVMe Fabrics Connect, which basically, at that point, it becomes an NVMe queue that runs on top of an NVMe Fabrics that runs on top of a TCP/IP transport. The data transfer model is should look very familiar if you know how other storage protocols work. If you look at the read transaction in the most general form, it would start from the host issuing a command capsule PDU that actually in the PDU it has an NVMe SQE that says I want to read a set of LBAs, and in return the controller would send a series of control to host data PDUs, which is free to slice and dice however it wants. It can be one big control to host data PDUs, or it can spread it into multiples. And after that, it will pipeline a response capsule PDU, which will, because TCP is an order delivery transport, we don't need to wait for the completion before we send the response capsule PDU. Host to controller PDU, that can differ within 2 use cases. If you have in-capsule data, which is an NVMe Fabrics concept that's not specifically to the TCP/IP transport binding, then the host would send the NVMe Fabrics command capsule, right, that has an NVMe SQE that says that it wants to write to a specific LBA or range of them, and it will have all the data payload with that command capsule. It's called in-capsule data. After that, the controller got all the data, so it will just send a response capsule back. And if the control, if the payload side exceeds the capabilities of in-capsule data that the controller exposed to the host, then we have our NVMe TCP credit mechanism that comes into play. The host sends a command capsule PDU that says, I want to write data to you. Then the controller is ready. It says that it will send an R2T back to the host, one or more, saying that I'm ready to accept X number of bytes from you with a given offset. And in return, the host will send a series of host-to-controller data PDUs. And that can reiterate for as long as, for the entire length of the NVMe command. And at the end of it, the controller will send back a response capsule PDU. So if you've seen other SCSI protocols before, or other protocols in general, it shouldn't come as a surprise. It's pretty much following one-to-one to the others.
Sagi, may I ask you a question?
Sure.
On the read versus the write.
So the response capsule is basically sent from the controller to the host saying, I'm done sending all the data to you. From my end, the request is completed, right? Because TCPIP guarantees us order delivery, then the response capsule, when the host will see that, it's guaranteed that all the data that was sent before that is guaranteed to arrive before. So the host can rely that it got all the data. A bit more about header and data digest. So this is inline data integrity or in-transit data integrity. For example, if your devices don't support T10diff or specifically for commands, NVMe commands that are not covered by T10diff. So we have transport level data and header integrity for that. They're different from their consequences on the TCPIP byte stream. For example, if your header digest or your header is corrupted, you found out that from the header digest, that gets you can't rely on the TCP byte stream anymore, so that's a fatal error. However, your data, if it's a failed data integrity test or the data digest does not match the CRC calculation on the data, then this is something that the transport can recover normal operation from. But in essence, all the payloads, all the bytes of the data, all the bytes of the PDUs are protected using data digest. And this is my last slide, and I think I'm right on time. So we have three classes of errors in NVMe. One is being the generic NVMe errors, which span, both fabrics and PCIe. Although I think that we do have some segments, but these are handled from the NVMe core architecture in the architecture model. We have NVMe over fabrics errors, which are related to regardless the transport binding that you're using. But we can also see specific NVMe over TCP errors, which can be either non-fatal or fatal. So I described, for example, that header digest can be a fatal error, which in that case you will probably terminate the connection and reflect to the other side what went wrong. But we do have non-fatal errors where we have specific status codes that reflect to the upper layer that it's sort of a transient transport related error codes, and they can be retried or recovered normal operation. So with that, I'll leave it here for Fred for multipathing improvements.
Perfect.
Okay, so I'm going to talk about the multipathing improvements that have gone into the last year or so since the last FMS that we had talked about some of this. The primary use cases are in fabrics. Fabrics are the primary places where you have multipathing. It's not often you have multiple PCI buses hooked up to the same PCI device, and so you don't get a lot of multipathing in the PCI environment. So the two TPs, the technical proposals we've been working on, are called TP 4004 and 4009. And those involve the addition of asymmetric access to the NVMe specification and the ability to describe the ways that subsystems can be divided back to the host. And that would be the divisions, the domains and divisions proposal. So if you think about a PCI card, it's kind of hard to cut it in half and still have half of it work. Well, if you've got something that's the size of this room, well, sure, half of it can stop working and the other half can keep working. And so that's part of the scaling aspect of NVMe and fabrics and larger NVMe systems. So with single pathing, that's what's always been there. You've got a single path, the road keeps going, you access your data, everything works fine. But if that road has a problem, you get a washout, they have to fix it, then you got a problem, you can't get at your data. So you can see that single pathing can have issues when you're talking about a large system that has lots of users, something the size of this room. So some examples of single pathing devices are primarily devices you'd see in your laptop or see in server systems that are, desk side kinds of systems where you don't have a lot of redundancy going on. With multipathing, the first thing that came along in version 1.1 of the NVMe spec was symmetric multipathing. And if you see this multi-lane highway here, very possibly a Southern California highway, or even Northern California highway, maybe that's 101. They're all just flying along there. Okay, so it can't be 101. They're actually moving. Okay? But they're all just going, and they're all going the same way. They're all going the same speed. Everybody's just moving along. There's lots of redundancy. If one path has a problem, you just switch to a different path. And so, in fact, yeah, when one of those lanes gets closed down, you just use a different one. They're all the same. They're all symmetric. That was the point of the 1.1 descriptions of multipathing. Everything's the same. They're all symmetric. With asymmetric access, you have something a little bit different going on. You have some set of paths which are faster than other paths. And the example case I've seen here, you see the same highway, but in fact, two of those lanes have toll booths on them. So all the traffic on those two lanes are going to have to slow down to be able to pay their toll. They don't have Easy Pass or whatever the automatic thing is they have at the San Francisco bridges there where you can just fly through. These are toll booths that make you slow down. So you've got some paths that are faster, some paths that are slower. And what we call those are some optimized paths or non-optimized paths. It's possible even that some of the paths are not accessible at all. So what we've done is created a way through the asymmetric access descriptions to be able to provide to the host information about that path state. Which ones are optimized, which ones are not optimized, which ones you can't even get to. So we have some information that's returned through the NVMe identification information, the identify command. We have the CMIC field, which tells you about the controller multipathing capabilities. So I've talked about room-size systems that are actually NVMe systems. So in those systems, they may be divided up into different portions. You've got different heads, which have their fabric connections to the hosts. You've got interconnects between those different heads, and you have different controllers in each of those heads. So if you look at this rack, it may be possible to have multiple power supplies. You've got multiple components. Some of those components are going to keep working, and other of those components may fail. So you've got the ability to divide those systems. Not only can they be divided, but the way that they're connected is part of what contributes to some of those different access characteristics. So you see in this case, through the different host ports connected to different heads, if you're accessing the storage that's connected to head 1 on namespace 1, you're going to have a little bit better performance if you use head number 1, port number 1, controller number 1. That's going to be your optimized access. But if you're using port number 2 to communicate with head 2, now you're going through the toll booth. You got to slow down a little bit to go across that hop that connects you over to the other controller where you can get access to the data. This is what drives some of the different performance characteristics that happen in an asymmetric system. Or in the case of paths which are inaccessible, you may have a third or a fourth or a fifth head which are simply not connected. In this case, head number 3 is down for maintenance. So it's going to have inaccessible paths to that data that's on namespace 1. If you look in the specification, you'll see pictures that look like this, where we see the two controllers, we see the multiple ports, the same namespace, but the data for that namespace resides on non-volatile memory that is associated with one side or the other. And so this kind of pictures are trying to show that capability. So we'll go on to talk about TP 4009, about domains and divisions. There's lots of different things. We had to come up with a name for these things. I mean, we could have called them territories or provinces or empires or all sorts of different stuff, but domains seem like a reasonable name. So basically what a domain is, something that has independent state. It's the smallest unit of unique state within a subsystem. One way to think of it is uniquely and independently powered so that you can shut off the power to it. So why would you want to do something like shut off the power to a part of your subsystem? Well, if you have a subsystem which is continually operational and you need to upgrade it, then you need to shut off part of it. Roll out the old part, roll in the new part, connect it back together again, and turn it on. Then you turn off the second part, roll it out, roll in the new part, power it, connect it up, power it back on again, and you're fully operational again with no disruption to your environment. But you have to be able to break the system into parts to be able to do that, and that's what divisions allow us to do. We take the domains within the system and divide it along those domain lines. So here we have our picture, again, of a large system. Here is a case where we have 4 domains, where we have 4 different power environments, where if we shut off anything within domain 1, then everything within domain 1 gets shut off, because that is a domain. That's the definition of a domain, something that has that unique state to that domain. So I've mentioned the non-disruptive rolling maintenance and upgrades. It allows us, for redundancy and performance reasons, to have all of the information unique to a particular domain stored with that domain so that it can be shut off, it can be maintained, it can be replaced, it can be updated. And we've provided ways for the host to be able to learn about this. Again, through the identify information, the host can find the domains. The host can then use that information if the host wants to create its own redundancy. It can find cases where having a mirrored set that it decides to create on 2 different namespaces might create a problem. Because if they're both in the same domain, then when it gets shut off, what kind of redundancy does the host have? It's going to lose both copies of the mirror. So the host wants to know, when it has 2 different domains, to put the 2 different halves of the mirror in 2 different domains within that NVM subsystem, so that they will get shut off, maintained, upgraded independently. So that kind of information is important to a host to be able to build an appropriately redundant system. So in summary, in multipathing, the things that we've added in the latest version of NVMe, the asymmetric capability, and the ability to describe fault boundaries and fault domains to the host system. So as Nick mentioned, with 1.1 of the Fabric spec, that's out in review. And the TP 4004 completed its review. That's integrated into the 1.4 revision of the spec. And TP 4009 with the fault boundary information, that is now in its 30-day review. So that should be out fairly quickly now. And we'll go on to the next of our presenters.
So I get to talk about discovery and transport improvements. I appreciate folks staying to the end, because this is not usually the most exciting thing. Not everybody wants to hear about low-level protocol and infrastructure plumbing. So we're going to talk about three important things under the covers in NVMe Fabric's 1.1 that are going to improve NVMe-oF implementations. The first is that we have a persistent controller support for discovery to notify hosts when the Fabric configuration changes. The second is Fabric IOQ deletion that does not take down the entire host controller association. And the third is an optional way to do flow control end-to-end instead of the current situation, Fabrics 1.0, which relies on submission queue flow control. It's an alternative flow control mechanism. So let's start with discovery. Persistent controller. If we look at Fabrics, the whole point of Discovery Controller is to tell the host what's out there. The host talks to Discovery Controller, it gets a list of NVM subsystems and Fabric ports to contact, it goes and contacts them. Very simple, one-shot discovery. The host goes out, figures out what to talk to, says thank you very much, and carries on. Question, what happens as that information changes? Well, it changes quite a bit. An interesting scenario is we've added a new port to a subsystem, and we need to tell the host about it. So the solution to that is what's called a persistent discovery controller, where the host keeps the connection to the discovery controller open, and then when we change something, the discovery controller can now send the host an async event that says, hey, something has changed. There's a new Fabric port has been added, and the host's response is to repeat the entire discovery sequence as if it just start over, and it now discovers the new Fabric ports. Instead of discovery being a one-shot process that happens once, it's now a continuous process where when there's an update, there's an async event to the host, and lather, rinse, repeat, the host goes through discovery and finds the new updates. Second thing is transport Fabric IO queue deletion. When we first to explain what's going on here, Sagi showed you a diagram that says that the way a host talks to a controller in NVMe Fabrics, NVMe, is has an admin queue and a whole bunch of IO queues. When we first did NVMe Fabrics in 1.0, we provided the ability to add new IO queues. The only way to get rid of IO queues was to take down the entire host controller association and then start over. Well, that's kind of a waste. All I wanted to do is get rid of one IO queue. I should be able to get rid of one IO queue. And that's what's been added in NVMe-oF 1.1. We have a new command called disconnect, which is the analog to connect. It takes a single IO queue and disconnects it. You can't disconnect the admin queue because it's kind of unique. If you take that down, the entire host controller association comes down, and so the net is disconnect is for IO queue management. If you have a problem with the admin queue, you do need to take the whole host to controller association down. This enables dynamic IO queue resource management. As the workload evolves over time, you can move resources that support IO among controllers in a large subsystem, such as the room-sized ones that Fred was showing a picture of. Oh, and while we were in there, I also get to tell the rest of the story that Sagi started when he pointed out that if you have a header digest error in NVMe for TCP, you've lost the TCP connection. Well, an additional thing we had to add in going to Fabrics 1.1 to support this use case is transport IO error containment. We need to have a biohazard bag into which we can put that dead TCP connection, and so it won't affect all the other connections that are still healthy. And that's exactly what's been done as part of the work on IO queue deletion. While we were in there, we also put in the support for unexpected IO queue termination, and this is a little bit of work because both the host and controller have to agree that the blast radius or the scope of an unrecoverable IO error, such as a digest failure for the header in NVMe over Fabrics over TCP, that blast radius of what comes down is just the IO connection that's gone. As Sagi said, you lose the TCP connection, you don't lose anything else. So this is negotiated when the admin queue is created because both the host and controller have to agree on the blast radius. Okay, so that takes care of the first part. I'm just going to talk about discovery and IO queue deletion. Now I'm going to talk about end-to-end flow control. This one's going to take a little bit longer because I first have to explain how submission flow control works. So this is how NVMe works in general. You have command queues, a submission queue and completion queue. They function as a pair. Commands flow through the submission queue downward from the host here to the controller. Command completions flow upward from the controller back to the host. And queue occupancy is fairly simple. NQ commands or responses the tail of queue, dequeue them from the head, and then have some way to return entries for reuse. And that, oh, by the way, have somebody return entries for reuse turns out to be the centerpiece of the story I'm going to tell here. So watch, this is going to keep appearing in the next few slides. So if you look at how this works on PCIe, the recipient manages queue occupancy. The recipient has a means of advancing the queue head to allow more commands to be submitted. Notice that this is done explicitly. The queue head is not advanced by command processing, and the queue head advanced mechanism depends on the direction. For the submission queue, the controller is returning entries to the host, so it just passes back a head pointer update in every completion that tells the host where the corresponding submission queue is. For a completion queue in PCIe, there's a doorbell. Now, when we took this over to NVMe Fabrics, PCIe doorbells don't transfer over well. NVMe Fabrics 1.1 was designed with submission queue flow control only, no completion queue flow control, so that the host has to be able to handle completions for all commands that has outstanding. And if the host can't handle more completions, it's really easy. It does not submit commands which it can't take care of the completion. And before I get people even more confused, this is NVMe Fabrics flow control. It's handling NVMe Fabrics level resources. If you get down into the transport, for example, TCP. TCP has its own flow control mechanisms that handle all of the TCP data, and they're separate. But again, here we go. We have to, how do we turn entries for reuse in NVMe Fabrics? We've got to deal with this head pointer update in each command completion. And that's exactly what was done in NVMe over Fabrics 1.0. Every command completion returns a head pointer update. This has a number of less than wonderful impacts on the transports. You have to maintain head pointer state at the host and controller in NVMe over Fabrics. The fabric has to be able to deliver completions, or at least those that contain these head pointer updates in order. And it prevents optimization for successful reads. One of the things we really wanted to do when we were working on the TCP transport was reuse a clever optimization from iSCSI. Most read commands just work. And so the queued optimization is on the last packet of data coming back. You set one bit in that last PDU data that says everything's okay at work, carry on, and then you don't have to send back response PDU. That's an optimization that is in the TCP transport that Sagi talked about. But none of these are possible if we keep having to send these annoying head pointer updates back. So don't send them. NVMe over Fabrics end-to-end flow control omits submission queue flow control. Now, this is not a free lunch. If you can only do flow control based on command submission, you have to size the transport resources to the maximum number of commands you're going to have outstanding on a queue pair, and that turns out to be static when the queue pair is created. So you lose a little bit of your ability to do dynamic resource management, but enables all the good things on the top half of this slide, and the flow control is now running end to end from the host submitting commands to getting completions back, and is resulting in all kinds of useful transport optimizations. So these are three of the low-level improvements in NVMe Fabrics 1.1. Persistent Discovery Controller, which gives us a standard way to tell hosts that something has changed, and they should redo discovery to find out what has changed. Fabric IO queue deletion, which allows us to dynamically manage IO queue resources, and as a bonus, we also put in transport IO error containment, the biohazard bag for failed IO connections. And end-to-end flow control, which enables transport optimizations. And a pleasant surprise for me when I started working on end-to-end flow control is it has turned out to be applicable to all three fabrics. Each one of the advantages I talked about applies to at least one of the fabrics, so that you can expect to see quite a bit of end-to-end flow control in implementations. And with that, be happy to take questions in the remaining time. Thank you very much.
So with that, we just wanted to open the floor for questions, anything with regard to the management interface or NVMe-oF. Just open.
Okay, I have some questions about NVMe. So my first question is, since the inbound interface has been proposed for 1.1 version, from the application level, there are SG utility and NVMe CLI are open sourced for Linux access to NVMe device or the enclosure. So which one is preferred for the inbound enclosure management?
Say that again?
I mean, in the latest 1.1 NVMe MI spec, the NVMe MI has added the SAS-related send and receive command, right? So from the application level's point of view, which tool will integrate this function? SG utility or NVMe CLI?
Oh, you mean you're talking about specific Linux utilities?
Yeah.
Yeah, I don't know. I think that NVMe, I'm not that familiar with the Linux tools, but I believe that NVMe CLI generally tries to put in support for all the administrative commands. And so if it doesn't support it already, I would expect that it could be added. And in the meantime, I think there's a way that the Linux NVMe drivers support a pass-through protocol, so you can kind of create your own commands and use that.
Sagi, did you want to add to that?
I will only add that we welcome patches, and if you're interested, you can submit a patch.
Okay. Thank you. Another question is about, as you can see, in the original version of NVMe MI, the out-of-band basically used for BMC to access the NVMe device, right? So if you have added the SAS-related commands in the NVMe MI message, so the target you are using is for enclosure management. But do you ever consider that BMC can use the SAS-related page as a communication channel? Because the out-of-band also transfers the NVMe MI message. If the NVMe MI message contains the SAS page, so it can also be used between BMC and the PCIe switch to talk the enclosure-related information. Because currently, vendors are defining their own protocol to implement. If your system has both BMC and PCIe switch, okay. So what's your point about this use case? Yeah.
Yeah, I mean, I think there's a lot of different ways to do it, and I think it's just going to be up to the folks making the system to choose what they want to do. So there's, as you mentioned, MI would be one way. You mentioned vendor proprietary methods is another one that switch vendors could implement. You could also use something like Redfish. And I think which one you choose, I think is going to depend on the particular application. But I think any three of those things would probably be fair game.
Okay, so the original purpose didn't consider the BMC.
I'd like to open the floor to other people that would like to ask questions. So feel free to follow up with Austin afterwards, and I think we're going to see if there's any other questions.
Okay, I'm done. Thank you.
Thank you. Are there any other questions?
It's about the relationship of the base spec activities and the fabric spec activities. I'm wondering if is it expected that like any new features that you add to the base spec, like some of the ones that you mentioned here with multipathing, are those expected to automatically become available for people to use in fabric's implementations, or is there some other follow-up process that's supposed to happen?
There's nothing that would prevent command set additions and things from the base spec being available for the fabric devices. That's always been the intent. There are some things which may be PCI specific. Some of the power management things are PCI specific. So no, they're not going to carry over. Our intention would always be to have the same capabilities. They may have to be done in different ways based on the transport, but we never do anything that is really targeted at just one environment. Some of that, I want to contradict myself a little bit. There are some times when vendors have specific needs and specific requirements that are targeted to specific environments. If something is only applicable to a U.2 form factor, sure, then that's the only place it's going to show up is on a PCI bus.
Okay. So I mean, if one of these TPs in the base spec gets approved and ratified, that's sufficient for someone doing fabric's implementation to go out and that's fair game now for.
Yes, primary example is if if you look at the numbering sequence, the ones that David mentioned were all 8,000 something.
Right.
Those are specifically targeted for the NVMe-oF document. The ones that are numbered 4,000 something are specifically targeted for the base specification. Right. And the ones that I mentioned, 4004 and 4009, while targeted for the base specification, are primarily intended for use on Fabric devices. You can create a PCI device with an over-the-top connector that goes into 2 different PCI slots that has asymmetric access characteristics. I know nobody that has any intention to go and build one of those.
Sure.
But the spec would let you.
I think one other thing that's worth pointing out is that going forward, the NVMe organization is working to actually refactor the specification, and the Fabric spec is going to be integrated into the base spec. We'll have the transports pulled out and the command sets pulled out into their own specs, but that core functionality is going to be done in such a way that it's combined. And so in the next revision of the specification that comes out, you'll see those changes.
A concrete example of what you're asking about is that in NVMe 1.4, we added a command called verify, which effectively does a read and discards the data just to make sure that the read worked. Sure. That was originally added, was motivated by SSDs. It is also completely acceptable to use it in Fabrics. It was defined in such a way that it's part of the command set that works for both PCIe and Fabrics, and that's a design pattern we tend to follow.
Perfect. Another question.
Actually, a couple of questions. So the first one is on the multipathing to Fred. So with the dual-ported NVMe drives coming up, so on a PCIe, standard PCIe, so would ANA be applicable to that, or how would the dual?
In most cases, I would expect not. In most cases, I would expect those to be symmetric devices that would have used the things that existed in 1.1. They would have used the CMIC field to indicate that they supported multiple controllers that could access the namespace. And all of the access to those is going to be the same no matter which port you use, which would meet the definition of symmetric.
So then the ordering for command processing is left to the host to determine which path it's going to...
If the host cares about ordering, then yeah, it's left to the host. Okay. The way the queues are managed, the way the spec describes how the queues are managed, once it's in the queue, the device can do whatever it wants.
Right.
There's no ordering constraints or requirements.
Okay. The second question, real quick, is to David about the persistent discovery controller. So it sounds like it's something very similar to RSCN handling in Fiber Channel. So where any state change notification you want the target device to in Fiber Channel, it's of course the Fabric. In case of NVMe, you're putting that functionality into the target device to push that async notification to say that something changed. Hey, come and rediscover me and figure out what changed. So is that limited to which hosts are seeing them, or is it like a blastogram that goes to all the nodes in the Fabric?
Because it's defined on a specific controller, this then becomes something for the implementation to optimize. Remember that a controller is associated with exactly one host.
Right.
And so the kind of refrigerator size, room size arrays that Fred talked about, that a number of companies build, can easily be implemented to, in effect, send the async event that corresponds to the RSCN only to the hosts that need to pay attention.
But if it is, if the change is such that impacts multiple controllers, meaning multiple associations, so then it needs to be handled it needs to be sent to all of them.
Then each discovery controller will send an async event to each host that has to take another look at discovery. Yes.
Right. Remember that it's the connection to the discovery controller. Mm-hmm. It's an async event on that connection. It's not on a normal login to a normal I/O controller where you're sending reads and writes.
That's true. Yeah. So basically, the host is going to keep that connection open forever in order to receive async notification.
And the good news is the host can use one discovery controller connection to support a whole bunch of I/O connections, and that helps a bit with scalability.
Right. Okay. All right. Thanks.
Okay. Any other questions?
Question of more basic understanding with the PDUs carried over TCP, once it reaches the Ethernet controller, does the TCP offload engine, is it able to place the PDU directly into the NVMe controller, or it has to place it first into system memory and then go through the same standard DMA process that's done in NVMe?
That's a good question. So from the standard, if I'm speaking from the standard side, nothing in the transport binding itself dictates where data is placed. It doesn't even dictate how PDUs are laid out into the individual TCP segments. But when you talk, basically, when you talk to a device that either is an Ethernet device, that you have TCP software that's running, TCP transport software that's running on top of it, that's handling the segmentation, or you have the NIC that's offloading, for example, the segmentation, then it's not really defined where the data is placed when it's reaching the controller. So, for example, you can have a single, NVMe TCP host that's talking to two different controllers, right? And then it said one PDU, and on one controller it has a software stack that's running on top of an Ethernet NIC. At that point, the PDU will actually reach host memory, be processed through the TCP stack, the NVMe TCP target, and then land into something like an SSD or storage, non-volatile storage. On the other controller, that could be an offload device that does a full, NVMe TCP protocol termination, and that happens to talk directly to something like an NVMe PCIe device in a peer-to-peer fashion. So from the protocol perspective, that's completely, it's not defining any of that. Yeah. That's really implementation specific.
Okay, and with that, we're going to need to conclude the session. Thank you guys very much for joining. If you have any questions, feel free to come up front and talk.